This is lecture 1, part 3 for Introduction to Systems Engineering and for System Thinking and Analysis. As always, we start our lectures with the list of references used in the material discussed. So the two references that we are using for this lecture are the Engineering Design of Systems, Models and Methods, and the textbook for the class Systems Engineering Principles and Practices, chapters 1 and 2. The agenda for this lecture is listed in this slide. We're going to start discussing the perspectives of systems engineering. Then we're going to move to discuss the systems domains. Then we are going to talk about systems engineering fields, systems engineering approaches, and finally, systems engineering activities and products. So let's begin with the first topic for today, which is the perspectives of systems engineering. A spectrum of views exists in understanding systems engineering. I mean, so far we have talked about all the point of view of a systems engineer, the interdisciplinary environment, the goals of a systems engineer in terms of leading a multidisciplinary team to achieve the development of a complex system. But a spectrum of views exists in understanding this field, from a general system thinking approach to problems to the developmental process approach for systems engineering, to the broad perspective of engineering systems. And we're going to talk about the difference between systems thinking, systems engineering, and engineering systems now. So first, system thinking is an approach to a problem, examines the domain and scope of the problem, and defines it in quantitative terms. From a system perspective, system thinking looks at the parameters that help define the problem. Through research and surveys, develops observations about the environment the problem exists. It generates all options that could address the problem also. Systems engineering focuses on the products and solutions of a problem with the intent to develop or build a system to address the problem. The approach tends to be more technical, seeking from potential future users and developers of the solution system. What are the top level needs, the requirements, and the concepts of operation? In systems engineering, attention is given to the subsystem interfaces and the need for viable and tangible results. Now, from the perspective of engineering systems, this is a broader and robust perspective to systems approaches to solve very extensive, complex engineering problems, integrating engineering, management, and social sciences approaches using advanced modeling methodologies. The intent is to tackle some of the society's grants challenges with significant global impact by investigating ways in which engineering systems behave and interact with one another, including social, economic, and environmental factors. This approach encompasses engineering, social science, and management processes without the implied rigidity of systems engineering. In the next slide, I'm going to show you an example of the type of problem that engineering systems is trying to tackle. So if you are not familiar with this, this was the Ebola outbreak that happened about 4 years ago. This was in 2017. And this is a similar situation like the one that we are experiencing right now. However, for Ebola, the way things were managed, were able to control the epidemic, and the situation got under control quite fast. So by January 17, I think I have some information here. This was for January 26. We can see the this representation, this dashboard showing where some of the cases were located. There were about 21,000 total cases in the world. The mortality rate was pretty high, 70%, almost 71%. And there were about 8,468 deaths in the world. And you can see that in the United States, there were many cases. However, the only confirmed were few, but there were many that were monitored because they were not necessarily, we were not necessarily sure that that was not a case. So comparing with our current situation, we're dealing with this new pandemic, this new outbreak, and you can see that there's a need for engineered systems that can help us deal with the current situation. You see that there's this dashboard is representing the COVID-19. This is by the Center for System Science and Engineering at Johns Hopkins University. And they are developing these dashboards to keep the statistics on the number of global cases, 100 million cases globally, when compared to 21,000 years ago. And you can see how those, this is showing the cumulative cases in red. And you can see how the United States is almost completely red because we have a big problem here in the States now. When compared to other countries like Africa, other continents like Africa, other countries like Canada, and so on. Okay, so the idea is that you can see that there are, this is as mentioned here, this is, so engineering systems investigates ways in which engineering systems behave and interact with one another, including social, economic, and environmental factors. So it's not just looking at the math or models, this also looking at other aspects of the problem, including the societal component, the economic component, and the environmental components that are needed for achieve this final solution. So this approach, engineering systems, encompass engineering, social science, and management, but it doesn't have the rigidity of the systems engineering approach. So going back to these three perspectives of systems engineering, or this comparison of system perspectives, like the one shown in table 2.1. So again, system thinking focus on process, the consideration of issues, evaluation of multiple factors and influences, and inclusion of patterns, relationships, and common understanding. Systems engineering focus on whole product, solve complex technical problems, and develop and test tangible system solutions. This approach or this perspective need to meet requirements, measure outcomes, and solve problems. Finally, we have engineering systems, which focus on both process and product. So it's a combination between system thinking and system engineering. Solve complex, interdisciplinary, technical, social, and management issues. This type of perspective has influenced policy, processes, and use systems engineering to develop system solutions. And finally, integrate human and technical domain dynamics and approaches. So now that we have an understanding about the perspectives of systems engineering, we can talk about the system domains. The engineering systems view encompass not only traditional engineering disciplines, but also technical, management, social, political, legal, and human domains. Traditional approach to system now encompass a growing domain breadth. This is much like a Rubik's Cube. The domain phases are now completely integrated into the systems engineering perspective of the big but complex picture. So we have management, engineering, technical, social, human, and political, legal. As we move in one direction, we are moving in the direction of systems. As we move in the other direction, which is more technical, we are moving in the engineering perspective. The system domain phases shown in the figure include not only the engineering, technical, and management domain, but also social, political, legal, and human domains. These later, softer dimensions require additional attention and research to fully understand their impact and utility in the system development. So now let's talk about some systems engineering fields. Engineering specialists look at systems engineering with a perspective more strongly from their engineering discipline. And we mentioned this in our first few lectures. Similarly, since systems engineering is a guide to design of systems often exercised in the context of a project or program, then functional project and senior managers will consider the management elements of planning and control to be key aspects of system development. The management support functions that are vital to systems engineering success, such as quality management, human resources or human resource management, and financial management, can all claim an integral role and perspective to the system development. So in this figure, we show some examples of systems engineering fields. So you see systems engineering is in the middle, and then there's a component or systems engineering is part of this management field. And then you have all these other fields connecting with at some point with systems engineering. So we have operation research, we have project management, human resources, quality control, architecture, control systems, and modeling and simulation. So the operation research view of systems engineering includes provision of a structure that will lead to a quantitative analysis of alternatives and optimal decisions. In diverse areas such as manufacturing and to autonomous systems, another interpretation of systems engineering comes from engineers who develop control systems, who lean heavily on the systems engineering principles that focus on management of interfaces and feedback systems. Another area that is also part of industrial engineering, like operation research, is modeling and simulation. And this provides a perspective that is integral to a cost-effective examination of systems options to meet the requirements and needs of the users. So in system simulation or in modeling and simulation, you'll build a computer representation of your system, and you can perform experiments in that model, and that will provide you with with feedback in terms of configurations. So if you have multiple configurations, you can apply that to your computer model, and then you can see the performance of those configurations. That is a cost-effective way of doing that examination, because you don't have to build a real system. You don't have to build a testing environment for that real system, which is very expensive. So you can perform all that analysis in the computer. So that's why it's a cost-effective examination of system options to meet the requirements and needs of the users. And so in addition to modeling and simulation, manufacturing and operational research, there are many other fields that are interacting, like the ones that we are showing in the figure: project management, control systems, architectures, quality, reliability, human resources, and so on. So now let's talk about systems engineering approaches. As the field of systems engineering matures and is used for many applications, several process models have been developed, including the linear, the V model, the spiral model, and the waterfall models. So now I'm going to describe these different models, process models, and their application to systems engineering. Systems engineering can also be viewed in terms of the depictions of the sequences or sequence of processes and methodologies used in the execution of the design, development, integration, and testing of a system. Early graphics were linear in the process flow, like the one that we are showing here. So you go from one point, you start with, let's say, the concept development, you complete that process, and then after you complete that process, then you move to the next step, engineering development. So you do all the tasks that are involved in the engineering development. After you complete that, then you move to the next stage. That's what we call linear in the process flow. There's no overlapping in terms of activities happening simultaneously. So there's no concept development and engineering development activities happening at the same time. You have one completed, then you move to the next one. Small variations are shown in the waterfall charts models that provide added means to illustrate interfaces and broader interactions. So that's what we are showing here. So see, now you have more interaction happening between stages in the process. Now you go from the bottom, you can go from the bottom to the top, or you can provide feedback to the stages that are before you. So that creates a variation when compared to the linear model that we shown on the previous slide. This is more close to what we are seeing currently in the systems engineering field. You have activities that are happening concurrently, and you have different teams working on different areas, and then you have collaboration among those areas, and all of them are moving forward in some degree, at some degree, until they achieve the final goal of developing the complete system. So the waterfall model, characterized by the sequential evolution of typical life cycle phases, allowing interaction only between adjacent phases. The waterfall model is known and discussed throughout the software and systems engineering communities, and is the basis for the military standard 2167A for software development. The major problem with the waterfall process is that iteration between phases that are widely separated is all too common. So here's the representation of a waterfall model. So you have that feedback between phases as represented by this figure until you get to the last step of the model. Another approach is called the spiral model. Many of the steps that are repeated and dependent on each other lead to the spiral or loop concentric diagram. So what happens here is that you have this center of the diagram, and you have these activities that are listed perpendicular to the center. And then the spiral model, and these are activities that are repeated through the system development. So what's going to happen is you have continuous, or you continuously visit each one of the steps in the process of the development. So let's say you start with mission and requirements analysis, then you move to functional analysis and concept formulation. But at some point after specification generation, you go back to the mission and requirements analysis. You go back and revise those, and you continue the process. You go through all the steps over and over again until you have completed the specification for your system. This spiral model addresses the need to shorten the time period between the user statement of requirements and the production of a useful product with which the users could interact. Too many system and software implementations were being produced and rejected because the development life cycle took too long. Valid requirements at the beginning of the cycle were no longer valid at the time of the delivery. And that's one of the things that we try to avoid. Like, again, if you look at the arrow pointing in with the neat word next to it, once you enter that loop, you're gonna be revisiting all these phases of the development. And at some point, you're gonna go back to the requirements. You're gonna make sure that those still valid, and then you continue with the definition and design of your system. So that's one of the good things about the spiral model. Valid requirements, or the requirements are kept up to date as the development continues. The spiral model has 4 major processes, starting in the top left and moving clockwise: design, evaluation and risk analysis, development and testing, and planning with stakeholder interaction and approval. These 4 processes are repeated as often as needed. The radial distance to any point on the spiral is directly proportional to the development cost at that point. So another representation of a spiral model is presented next. So as you can see, this is not a perfect cycle. So what that means is, as you move into the spiral, obviously you want to get to the middle to complete your process or your development. But you can see that some of the areas are farther away from the center, and that basically is representing that there's an additional cost when compared to other areas of the development. And as you can see here, you enter the spiral and then you are revisiting some of the steps of the process. You're making sure that everybody is up to date with the development, and then you get to the final point of the development, which is the center of the diagram. This is I apologize because the diagram is not showing very well. So you can refer to the PowerPoint notes. In the diagram should show better in the PDF file. But what we have here is called the B diagram. The Popular Systems Engineering B diagram provides a view of life cycle development with explicit relationship shown between requirements and system definition and developed and validated product. So in this, you have a V shape, and each one of the areas of this V shape is representing a step of the process. On the next slide, we have a better representation of a V diagram. This one shows the design and integration process as a V, with the emphasis of this model of the engineering process for the system being on the activities that the engineers perform. So this V diagram, at the bottom, you see the time. There's an arrow representing the time. So as you move from left to right, that's the timeline. So those activities that are happening towards the left, those are the initial activities of the development. And then as you move towards the right, those are the latest activities for the development. So in here, the process is initiated at the top left of the V with the definition of the operational need of the stakeholders. The focus of the decomposition and definition process or design is the movement from an operational need to system level requirements, to specifications for each component, to the specifications or specs. The horizontal line drawn just under the middle intersection of the V depicts the handoff of the final products of the design process to the discipline or design engineers. Those engineers whose orientation is electrical, mechanical, civil, chemical, aerospace, computer science, and the like, and whose job is to produce a physical entity. The right-hand side of the V depicts the integration and qualification activities of the engineering of a system. Integration involves the assembly of the components, the assembly of lower level components into higher level components, and the assembly of high level components into the system. All of this assembly involves testing or qualification of the newly assembled system elements to determine whether the assembled element meets the requirements or spec that the design phase has established for that element. This qualification is called verification. A broader perspective is shown in this figure, provides a full life cycle view and includes the management activities in each phase of the development. This perspective illustrates the close relationship between management planning and control and the systems engineering process. So in this figure, you can see there are these dark gray boxes that are part of larger boxes that are light gray. If you start at the top towards the left, you have the need analysis light gray box. Okay, and they have some of the activities that are performed in the need analysis. You're basically looking at the customer requirements and also looking at concept, the new product idea, and the technology push. So from there, we have discussions and collaboration, and we have also brainstorming. We move to the concept exploration, where we get a market assessment, and we have a preliminary system product concept definition. Once the concept explorations phase is completed, we move to the right, where we have the concept and program definition. And there are some activities that are happening in this phase, including the proposal, pricing estimation, statement of work, product definition, the functional system block diagram, or the functional system design. We're going to talk about that later in this semester. The work breakdown structure, the risk assessment, and the budget and schedules. From there, we move to design, technology, validation, engineering, development. From there, we move to product manufacturing, technical support and operational support. And then finally, we move to the system use. So, so in the next few lectures, we're going to start looking at some of these areas of the systems engineering process, and also look at these approaches as part of our discussion. And that's the last slide for today. These are the topics that we cover, and let me know if you have any questions.